Okay, thank you for the presentation and good afternoon to all. I'm Leandro Lucangeli, and in this presentation I want to show you the paper entitled SISTINE 2.0 Sensorized Socks for Postural Telemonitoring. The work was carried out in collaboration with Professor Valentina Camomilla of the University of Hidalgo and with Professor Antonio Pallotti and Engineer Emanuele D'Angiantonio of the Tecnoscience Parco Scientifico e Tecnologico Continuo. In this presentation, I will first describe the motivations and the goals of this study, then focus on the state of art of posture and of the wearable devices used for this assessment will be shown. So the materials used in the construction of SISTINE system and the methods supporting the development will be presented. Then I will describe the construction phases of the system and a pilot study conducted for the assessment of posture. Finally, the result and the future development will be presented. In the first section, I will describe the reason and the objective of this work. In particular, the goal of this research project is the development of a wearable system for telemonitoring. For this reason, the literature was analyzed, and it emerged that all those services that provide remote medical treatment can be defined as telemedicine programs. A key rule in the provision of this service is given to the technology that can ensure service is accessible to all, economically sustainable, and efficient. In these programs are particularly interesting in the case of chronic disease that require periodic medical services that have an high cost for the health system. The telemonitoring is, for example, used for patients with cardiovascular disease, peripheral vascular disease, and respiratory disease. To support the delivery of this service, technologies are spreading in on a large scale, and the sensors can provide useful parameters for monitoring, for example, blood oxygenation levels and or cardiac activity. For this work, a focus was made on the wearable devices in the analysis of posture. Posture analysis is carried out to prevent problems related to the spine and musculoskeletal system, but also to assess the risk of falling, for example, in the elderly population. The devices that are commonly used are force platform and baropodometric platform, and the parameters that are usually extracted are the center of pressure and other parameters related to it. A low-cost alternative of these devices is the use of the timing, inertial sensors, and wearable devices. So in this third section, I will describe the materials and the methods involved in the development of SISTINE 2.0. And so the second version of SISTINE takes up to the work described in Metro in the 2021 conference and include some updates of the devices. A commercial sock was selected, and on it is integrated force sensors and inertial sensors. In the second version of this device, two socks were used, one for left foot and one for the right foot. Another important update is the use of the belt, on which an Arduino Nano microcontroller has been placed at the height of the pelvis. The system is completed by hardware and software devices, such as a module Bluetooth for the connectivity, a battery for the powering, a smartphone for data user interface, and a database for storing, and software for data processing. In addition, a force platform was used as a gold standard in the pilot study which will be described in section 5. The methods include conditioning and calibration operation. For signal conditioning, a circuit with an operational amplifier in a non-inverting configuration was used. For the force sensor, and for the HIMU, it was not necessary to condition the signals because this sensor is already integrated in an appropriate electronic board. The calibration is then necessary to obtain information on physical quantities measured by sensor. For the force sensor, no masses were applied to the sensors in different configuration, no layer, single layer, and double layer of fabric to simulate the behavior of the sensor once applied to the socks. For the initial sensor, an automatic calibration was carried out when the device is turned on. After selecting the materials and implementing the methods, I defined the system design. So the existing system includes several units, an acquisition unit, a transmission unit, a storage unit, and an elaboration unit, and consists of 3 wearables. The acquisition and transmission unit are specific to each wearable, while the storage and the elaboration unit are unique for the system. Once the socks and belt were chosen, four sensors are applied to the sock, and in accordance to the literature regarding the areas of the grid plantar pressure. The INU is applied near the malleolus in the external part of the leg. In the same way, the Arduino Nano board was positioned on the belt at the height of the pelvis. The electronic circuit was designed and then implemented in a breadboard, so it was inserted into a 3D printing. The last part of the acquisition unit involves the use of the Arduino board for the acquisition of information from sensor and transmission of the via Bluetooth at 32 Hz. The transmission unit consists in the use of a smartphone and an Android application developed in Meetup Inventor, which specifically perform 3 main operations. The connection with peripheral devices via Bluetooth, the sending of the collected data to a database or to smartphone memory, and finally the possibility of visualization of data collected in real time. The data can be stored in these two ways. In an alternative way, but also in simultaneous ways. The data is organized to provide 4 files containing the information of left sock, right sock, belt, and the sample rate. Then the data can be used for the processing. An algorithm was created to perform several operations, such as the reception, the visualization, and the extraction of some parameters. This algorithm works in MATLAB and in Colab to guarantee accessibility, even remotely, to all the person authorized to process the data. Okay, I will describe in this section a pilot study that we conduct. SISTINE was used. The aim of the Pallotti study is the evaluation of the quality of posture analysis performed by SISTINE. And the plan consists in the evaluation on 8 young and healthy participants during the execution of static tests to ensure the clinical applicability of the system. The project was approved by an ethics committee, and each participant signed an informed consent. About the test protocol, the participants were required to remain still in upright position with his gaze fixed forward for 2 minutes, and the test was repeated 3 times. The feet were placed separately on 2 platforms, horse platform, in a comfortable position. Once the tests were carried out, the data were analyzed. After filtering and synchronizing the SISTINE and force platform signals, the pressure center was calculated. For the socks, it was found as a weight average, and for the force platform, it was calculated with the ratio between force and moment. After the COP was calculated, 5 parameters were extracted: the anteroposterior range, the mediolateral range, the measure minor and the area of the confidence ellipse. For this last section, I present the result. In particular, the data permit to build the images of the COP trend or for the evaluation of plantar pressure. And furthermore, the SISTINE error values for the COP have been calculated and reported in the graph on the right, according to the reference of the force platform. Of the 5 parameters extracted, the minor axis and the area of the confidence ellipse were excluded because they assumed an error value about 100%. For the anterior posterior range, we have an average error of 7 millimeters. And for the mediolateral range, we have an error of 2 millimeters. The graph on the right shows the SISTINE error values for the main axis of the ellipse, looked for participants. This description of data was made to evaluate the individual variability for the different parameters extracted. It is evident that the error is also dependent on the individual participant and often comparable with the variability of the reference system. In conclusion, the SISTINE system seems to provide a good indication of the balance, even if the SOCs tend to overestimate the COP and other parameters. In particular, the system could be used to monitor posture over time and prevent complication in for example, the elderly population. Future development include a validation study with respect to the barometric platform, and the comparative analysis between the accelerometric signals of the pelvis with the COP calculated by SISTINE. Furthermore, tests will be carried out in perturbed condition, open eyes and closed eyes, to evaluate and predict the risk of fall in the elderly population. And so finally, this device will be used also in other applications, for example, the walking or on the sport. Thank you for the attention.